Thank you. It's always a great pleasure to be here in Wien. Thanks organizers for the invitation. So you see that the talk is a bit chaotic because I do not have any one main story, but I will be talking about several interesting things, and then maybe the main message will be that 2D magnetic materials can be interesting from very different point of view. And so first I will start with some which everybody had something about, problems with statistical mechanics, so-called Mermin-Wagner theorem. Do you have long-range order or you do not have? And also I have to say that this common understanding is not always accurate and complete. So that is why I think we need to reconsider it more carefully. Then I will tell the story of our false start, because actually I think people who are doing electronic structure calculations, they are always very proud to tell that, aha, we predicted something and then experiment follows along the same direction. But we all know that in many cases things go in completely wrong way, different way, but nobody never tell about this, and I think general impression turns out to be distorted. So I will tell about our first attempt to discover two-dimensional magnetism and how it goes in reality. Then I will be talking about chromium trihalides. It is the most popular family of two-dimensional magnetic materials, therefore it is not surprising that I will be talking about many stories about this material. And then at the very end, more briefly, I will tell two other materials just to demonstrate diversity of the world of two-dimensional materials, because difference with chromium sulfur bromide is that it is extremely highly anisotropic, and then it has important consequences, especially for optics. And then I will tell about iron, germanium, tellurium. Again, the difference with chromium trihalides is that it is metallic, whereas chromium trihalides are semiconducting, and again, it will lead to some difficulties. So first of all, let's tell, for some of you it will be just reminder, for some of you maybe something will be new. Then two-dimensional magnets, if it is strictly two-dimensional magnets, they are dramatically different in the sense of their behavior at finite temperatures in comparison with conventional two-dimensional, three-dimensional magnetic materials. Everybody heard about so-called Mermin-Wagner theorem, which was a kind of rigorous, proof that in Heisenberg model, in two-dimensional Heisenberg model, there is no long-range order at finite temperature. What actually happens with Heisenberg model, two-dimensional Heisenberg model at finite but small temperatures, it is another interesting story. I think the first theory was developed by Polyakov, actually in the context of quantum field theory. It turns out that you do not have long-range order, but you have short-range order with a correlation length which is exponentially large at small temperatures. And actually it turns out that for many observables it is basically the same. Then the point how to proceed with quasi-two-dimensional magnets. What do you mean? What do I mean? So either if you are not exactly in two dimension, you have some very weak but finite interaction between different layers, you have quasi-two-dimensional materials. In this case, literally speaking, Mermin-Wagner theorem is not applicable, and you will have some short-range order, but still you have anomalously strong fluctuations, you will have some suppression of Curie on AL temperature and so on. Or if you have easy axis anisotropy, then again conditions, sorry, no. Huh? Sorry, what shall I do? Hmm? I don't know. Okay, thanks a lot. When you have quasi-two-dimensional magnets, then conventional theory of three-dimensional magnetism does not work. You need to take into account these very strong fluctuations. And I would say the most practical way to take it into account it is to use so-called self-consistent spin wave theory, because in just conventional theory of three-dimensional magnetism, the simplest approximation which you can have it is mean field, when you introduce just some other parameter associated to long-range order. As I said, in quasi-two-dimensional magnets, there is some temperature range where you have long-range order, but then there is also some temperature range where you do not have long-range order, but you have some kind of short-range order. And in this self-consistent spin wave theory, you introduce some other parameter describing short-range order, which is approximation, but nevertheless, it allows you to do some true calculations. There are different ways. How you to do it. And I will follow our old paper with Valery Irhin and Andrei Katanin. So suppose you have quasi-two-dimensional magnet as it is shown here. You have Heisenberg terms. You have, in principle, some anisotropic exchange interactions, and you have easy axis anisotropy. And then, in principle, you can consider truly two-dimensional system or quasi two-dimensional system. It will be just a different JJ. Then there are many ways to build this theory. The way which we used, it is used so-called Berlechtar-Krivoruchka-Yablonsky representation for spin operators. It is slightly better than Halstein-Primakov or Dyson-Maleev, which everybody knows. So when you reproduce spin operators in this theory, you introduce not only bosonic operators, but also fermionic operators with slightly improved description at finite temperature. Then you substitute all this in the Hamiltonian, or alternatively, you can use so-called Schwinger bosons. It's more or less the same, but I will discuss this. But as I said, what is important that you introduce short-range order parameter gamma, which describes pairing, of magnon operators not at the same site, but on different sites. And just when you use the self-consistent equations of self-consistent spin wave theory, if you solve them numerically, what you really see is that when you go to very small two-dimensional anisotropic, then Curie temperature goes down. I'm sorry, I'm afraid it's opposite. J prime equal J is 1 and so on. So the more two-dimensional magnet, the lower is Curie temperature. But you have also short-range order parameter, and short-range order parameter survives at much higher temperatures, and then you can use it to describe everything. This theory is not accurate. Then you can use some kind of ladder diagram corrections, and at the very end, you are able to calculate Curie or Néel temperature in different types of magnets. And after corrections, sometimes you have even some reasonable agreement with experiments. So it is a kind of tool to describe quasi-two-dimensional magnets. When you have, contrary to exact case of Mermin-Wagner theorem, you have some long-range order, but at much smaller temperatures. And by the way, unfortunately, in 1999, as follows from this table, I knew already about chromium 3 bromide. Why it is unfortunately? Okay. Before then, I want to say why everybody misunderstood this. The point is the following. It is the role of dipole-dipole interactions, and it is relevant for true two-dimensional materials. Because if you look at some kind of standard textbooks and many papers, everybody believes that dipole-dipole interactions result in shape anisotropy. So if you have just one plane, that dipole-dipole interactions will push all spins lying in plane, and then you have this Brzezinski-Kosterlitz-Staulis theory for easy plane anisotropy and so on and so forth. But I have to say that it is totally wrong. Dipole-dipole interaction coincides with shape anisotropy only for very special situation. Homogeneous magnetization and ellipsoidal sample. Statistical mechanics is completely different. The first, I think it was noticed by Maleev long ago. And the difference that when you just calculate spin wave spectrum for ferromagnet with dipole-dipole interactions and with easy axis anisotropy, behavior of spin waves completely different. You have k square at small q for easy plane anisotropy, and you have square root of q for dipole-dipole. That is why Maleev hypothesized that you have true long-range order. This system with dipole-dipole interactions, Mermin-Wagner theorem is not applicable for some reasons. Later we reconsider it in terms of cell-consistent spin wave theory, and we confirm this conclusion in cell-consistent spin wave theory for the ferromagnet with dipole-dipole interactions. You have truly long-range order, but strange enough, in our work, we found that transition between ferromagnetic and paramagnetic phase is of the first order. I still do not know, is it physical reality or it is artifact of approximation, but anyway, something worth to keep in mind. Why I spend time for this? Because as you will see very soon, it is relevant to discuss what you can expect, for instance, in Chromium chlorine 3. Okay, then why I said that unfortunately I knew about chromium bromide 3, because I think the story of two-dimensional magnetism was started when I was in Manchester. We had discussions with Kostya Novoselov, and in what is discussions that, probably it is a good idea to take some layered ferromagnet to antiferromagnet, extract one layer, and then you can use it and so on. But what kind of ferromagnet to use, we do not know. And more or less randomly, I suggested to choose potassium 2 kappa fluorine 4, quasi-two-dimensional perovskite, because I knew already that it is very two-dimensional. We did density functional calculations, so we found that cohesive energy when you try to exfoliate one layer is just 2 or 3 times larger than for graphene, so probably it should be possible to exfoliate. And then we calculate electronic structure, we calculate parameters, we estimated, it turns out to be easy plane anisotropy, we estimated Kosterlitz-Staulis temperature, and so on and so forth. Temperature is pretty low, but still it is possible, but nobody never worked with this system, because it turns out more or less in that time people started this chromium trihalides, which becomes very popular. But in principle, why would not try this now? Because it is still interesting system. It is spin 1/2. It is Kosterlitz-Staulis system, and so on and so forth. But nevertheless, it was really false start because we described everything very correctly, except we did not guess what kind of system to choose. Sometimes it happens. Okay, but Chromium X3, due to a huge experimental activity, turns out to be really the most popular family of two-dimensional materials, and I will tell a few stories about this. First of all, electronic structure. I mean, as usual, it's very important question. Can you use density function or you cannot? And we considered it quite systematically from different sides. We did DFT plus U, of course, as everybody. We did dynamical mean field theory, and we did methods based on GW, quasi-particle self-consistent GW in collaboration with Mark Shilgarde and Svagata Acharya, who in that time was working in our group in Nijmegen. So we considered this equation from different types, and the message is that correlation effects are important. And the most important point, first of all, DFT plus U forget. Totally wrong for this particular system. Even DFT and some more advanced methods like DFT plus DMFT or DFT or GW based methods, they have much closer results at DFT plus U. But the most important point, of course, the value of gap is totally different, but it's normal. You have gap problem in semiconductors. Density function always give you too small number of gaps and GW fix it. As you see, number of gaps really different. But the most important difference is about description of valence band. The composition between orbital composition of whole states. The role of ligands, halogen ligands, and the role of d electrons of chromium. And this is very important for the future. And density functional is not accurate, but methods like GW seems to be accurate enough. And the conclusion is quite simple, that when you go from chlorine to bromine to iodine, PD hybridization increases, and you have more and more contribution of halogens in whole states. Electronic band structure is not sensitive. Electronic band structure. Then, since we were able to add also vertex excitonic effects based on GW, we solved Bethe-Salpeter equations, and we were able to describe optics with excitons, and we were able to describe excitons. You see this orange absorption is done with excitons with vertex correction, and green is just convolution G dot G, so just single particle excitations. And as you see, the effects of excitons are quite important. Interestingly, that you can also analyze based on solution of Bethe-Salpeter equation what kind of excitons do you have, because you know two limiting cases. One is so-called Frenkel excitons, when electron excites and stays in the same site, so it is really local tonside excitation. Another opposite limit is so-called Wannier-Mott excitons, where electron and hole, the distance between them are much larger than interatomic distance, and they are coupled by Coulomb interaction. In a sense, all these chromium trihalides, they are in between, but closer to Frenkel limit. So in principle, in chlorine case, it is almost local. When you consider bromine and iodine, you see that it is a kind of wave function in excitons. It is slightly more, but to compare, it is calculation by the same method for molybdenum disulfide, where you have more or less conventional Wannier-Mott exciton, and you see that it is just completely different orders of magnitude of parameters. So the main point that excitons are not completely localized, but are rather localized. And then this is a work what we did with a group of Kostya Novoselov and Maciek Kapersky in Singapore. It turns out to be that experimentally they found, when they consider photoluminescence at exciton spectra in the presence of magnetic field, it turns out that bromide and iodide behave completely different. So you can really see what is a sign of PD exchange coupling within the exciton. And it turns out that, first of all, it is different for different types of excitons, and second, it is different and opposite for bromide and for iodide. And it was not easy to understand. Again, this is a very detailed presentation of this exciton wave function, compositions, but you do not see any dramatic differences. As I said, in the case of iodide, exciton is a bit less localized, a bit less contribution on interchromium DD transition and more DP, but it is not dramatic. But nevertheless, it has important consequences, because it turns out that effective DP hybridization depends on energy. Roughly speaking, you have two limits, right? If you have just interatomic, truly, if it would be truly Frenkel exciton, then you would have just Hund exchange, and you have just ferromagnetic coupling between PD. If you have pure hybridization, then Schlifer-Wolf transformation, you have antiferromagnetic. Here you have something in between. And it's really funny. It turns out that when you go along valence band, that the effective sign on PD interaction depends on energy. So On the top of valence band, where hybridization is very high, it is antiferromagnetic, but then when you go further and further and further, it is more ferromagnetic, and this all kind of subtlety leads to dramatically different experimental behavior in the sense of excitons in magnetic field. I think it is funny. Then, what about magnetic anisotropy, Kitaev, and other exotic interactions? We did it in all methods, I mean, what we used. The results are not dramatically different, but as I said, correlation effects are important. Therefore, very recently with the work by Oleg Yazev, I participated slightly in this work. It was done just quantum chemical calculations. Of course, you consider a relatively small system, but the small system you solve in a sense exactly. Therefore, the results what you will have, they are basically, probably you should trust them. Okay, so you see that we take into account single ionic anisotropy and isotropic exchange, Kitaev exchange, symmetric, antisymmetric path, and so on and so forth. And it was all calculated for the small cluster. And the conclusions are that Heisenberg model is okay. This J2, which corresponds to biquadratic exchange, is always much smaller than J1. Kitaev exchange and all other kinds of exchanges are negligible, very, very small. And as for anisotropy, it turns out to be the following. Magnetocrystalline anisotropy always out of plane in all these three compounds. But for the case of chloride, it is much, much smaller than dipole-dipole anisotropy, shape anisotropy. Therefore, most of people would believe, and I think some people still believe, that chloride should demonstrate Kosterlitz-Taulis behavior and so on and so forth. I do not believe. Following Maleev and our work, it is shape anisotropy, but it behaves differently. I believe that in chromium chloride 3 in single layer, it still should be some long-range order, and it can be even very interesting system to study experimentally the difference between shape anisotropy and dipole-dipole interactions. That is why it is interesting. And in bromide, you have almost complete compensation. Therefore, it seems that taking in finite accuracy, it can be actually everything. As I know, experimentally, most of experimentally says that you always also have some out-of-plane spin directions. And in iodide, it is again very clear situation when magnetic easy axis anisotropy is much, much larger. Okay, this is an interesting story. Okay. Then the last story what I want to tell you about these trihalides, it is a story about magnetic polaron or ferron or whatever. Different people use different names, but the point is the following. Suppose you have magnetic semiconductor. It can be ferromagnetic, antiferromagnetic, paramagnetic. But when you introduce some small amount of charge carriers, electrons or holes, this small amount always prefer a ferromagnetic environment. This was formulated first like Zener, we know it is a double exchange. So just when electron moves in environment with parallel spins, it has a gain in kinetic energy. Then it is partially supported by so-called Nagaoka theorem. Then you can derive some Hamiltonian. This I just wrote, okay, it's a bit ugly, but just some Hamiltonian, which we derived long ago, considering Hubbard model on Bethe lattice. Then you can derive different terms, and you really see that you have this double exchange contribution from excess electrons. And what is really important is that from analysis of this and other Hamiltonians, you can come to the conclusion that when number of conduction electrons is not sufficient to make complete ferromagnetic order, it still can form some kind of ferromagnetic droplets, which sometimes called ferron, magnetic polaron, and so on and so forth. And immediately we applied, and technically it is much, much simpler than the work which I was talking about before. We applied it to bilayer chromium iodide 3, because bilayer chromium iodide 3, contrary to bulk chromium iodide 3, has antiferromagnetic coupling between layers, because it has different stacking. So what we just consider, let's assume that electron or hole creates around itself some kind of ferromagnetic droplet. Then we can estimate what is energy gain. Energy gain is the gain in kinetic energy in the band age. But energy loss is that you have the squeezed electron wave functions, you have 0-point fluctuations, which goes energy up. And then since matrix is antiferromagnetic, then you lose, of course, exchange energy. Then you need to minimize, then you need to find optimal radius, then you need to see whether total energy is negative or positive. We did these calculations, what we found that it is a kind of prediction that when you have electron doping, then in bilayer chromium iodide, formation of ferron should be possible. Then it means that if you will try to dope bilayer chromium iodide electronically, then it will be this after trapping, self-trapping, then very low mobility and so on, whereas holes will be normal. I think it's a kind of also interesting prediction. That's all for chromium trihalides. How much time do you have? Okay, thanks. Okay, but two other stories will be shorter. As I said, chromium trihalides is the best studied system, and also we did the most. But I have to mention two other systems, and one system is chromium sulfur bromide. It is also semiconductor, but what is important difference, and it has some experimental consequences, as I will show very soon, that contrary to chromium trihalides is extremely anisotropic. It is very, very, very anisotropic. Okay, then we use this chromium as bromine to answer the following questions. I mean, exchange interactions, of course, are dependent on Coulomb interactions, intersite, intrasite, all kinds of interactions. And in two-dimensional materials, this effective Coulomb interaction are very sensitive to screening. So in particular, if you change substrate or something like that, you can change Coulomb parameters. And then the question is, can you manipulate magnetic properties, manipulating substrates, manipulating screening environment? To do this, we did the following calculations. First, I think many of you know the modern way to calculate effective interaction parameters for many body models. It is so-called constraint RPA. When you take into account all screening processes except screening by correlated electrons to correlated hole transitions themselves, then you can also modify this method to take into account just in a continuum medium way, just substrate or whatever. With this way, we calculated parameters, effective Hubbard parameters, U prime, and J Hubbard, three parameters which you have in so-called Kanamori model, simplest multi-band generalization of Hubbard model, as a function of dielectric permittivity of environment. And not surprisingly, the stronger screening, the larger dielectric constant, the smaller are all these parameters, that in principle can be changed in a kind of quite broad interval. Okay, then we use this model to calculate effective magnetic parameters. So we introduce Heisenberg path, we introduce single ionic anisotropy. Since it is strongly anisotropic system, then you have at least two anisotropic constants, D and T. Then you have anisotropic exchange, and then of course you have dipole-dipole interaction. Mostly, of course, we use our favorite method based on magnetic force theorem, but in that case we just feed parameters to difference of total energies. Why not? Nothing is wrong with this. We considered the dependence of exchange parameters on effective U, and effective U, as I have shown, you can change playing with substrate. Also, we considered anisotropic exchange, which turns out to be negligible everywhere, but single-site anisotropy constants, they turns out to be very strongly dependent on effective U. things, and then sometimes it can even change the sign. And so we calculated dependence of magnon spectra, TC, magnetization as a function of temperature. And the point is that combining CRPA with model calculations of magnetic Hamiltonians for two-dimensional materials, you really can study how tunable is this. Then, yeah, I am afraid, like, how much time? Not much. Okay, then let me skip the rest, because the rest will be about that in chromium S bromide you have so-called hyperbolic excitons, experimentally observed. I explained what is hyperbolic excitons. It is some kind of electromagnetic waves which you can have only in very strongly anisotropic material when you have dielectric function positive in one direction and negative in another one. And it was some kind of experimental work by Dima Basov group from Columbia University, which confirms this. Okay, then the very last point which I want to tell, it is about ferromagnetic material, and it will be the story about the role of phonons. Because when you consider magnetic effects on electronic transport and other things, there is a direct effect due to electron-magnon scattering, and there is indirect effect due to dependence of electron-phonon scattering on magnetic state. This we studied, blah, blah, blah. Okay, calculated exchange parameters, calculated thermodynamics, calculated everything. And the answer is very simple, that if you direct scattering of magnons is very, very small effect. But direct scattering on phonons is dependent on magnetization and therefore on temperature, because just electronic structure is dependent on temperature. And this is much, much stronger effect. I think it's a kind of important conclusion. And then the very last point, we looked how this electron-phonon interactions affects on exchange parameters. We use the method which we developed long ago with Sasha Lichtenstein. Recently, we published a very big review. I just refer to it. And what we did, we have a formula for exchange which depends on self-energy and green function. And what we did, very simple things. We just insert the contribution of electron-phonon interaction into self-energy and green function. And we found not a very big effect, but kind of 10% effect in Curie temperature and effect in magnon spectrum. So I think it's also a very nice way to consider electron-phonon interactions. I think I do not have time to go point by point, but I hope I convinced you that in physics of two-dimensional magnets, many. That's all. Thanks.